who's presenting a talk today entitled Under the Ridge, Looking Below the Seafloor with Stable Isotopes. Desiree and I met during a conference, actually, one of the prime examples of in-person conferences a while ago. And we've been working together since, working on a large proposal for the European Union, together with other colleagues that are being in the audience as I see today. Desiree did her degree, her bachelor's and her master's degree at Utrecht University in the Netherlands, finishing in 2008, and followed by a PhD at the same institution, 2009 to 2013, in Archean geology and sulfur isotope geochemistry. And then she moved straight away, pretty much, to the University of Bergen, where she is today as an associate professor in analytical geochemistry. And she's also part of the famous KG Jepsen Center for Deep Sea Research, which...
Oh.
Neil has muted me now. That was
sorry
not,
about that.
I think, what he intended to do, but that's all right.
Sorry about that.
Where she's now. And I think the Jepsen Center for Deep Sea Research is also part of the Department of Earth Science at the University of Bergen, or somehow interrelated with one another. But without further ado, Desiree, the stage is yours. The talk will be recorded for all of you. The questions will not be, so once we are moving to the question session, you can ask questions through the chat or by raising your hand. Please, if you do so in the question session, switch on your camera system so Desiree actually knows whom she's talking to. But we will disable the microphones and the camera systems during the presentation. Only the conveners will stay online, so Desiree has something to look at during the talk. Desiree, stage is all yours.
Okay, thanks very much, Christophe, and well, thanks again for inviting me to talk here today. So I want to take you guys. Sorry, too many screens. I want to take you guys today to these amazing hydrothermal vents on the seafloor. So here you see some black smokers from different geological settings, from fast spreading to ultra slow spreading to back-arc basins, all venting fluid over 300 degrees, forming sulfite-rich and spectacular chimneys. And what I want to do today is basically go through how we can use stable isotopes to try and understand what is happening below the seafloor in these locations. So it's going to be a little bit back to the basics with some new stuff, so that you guys will all become sulfur isotope experts at the end. Now, we actually have quite a good sort of general model on how these seafloor hot springs are formed. So we basically start with cold seawater that percolates through fractures in the oceanic crust, and then it gets heated up at depth by the presence of a magma body. And this results, for example, in the loss of sulfate through precipitation of anhydride on the way down. And in the reaction zone, we lead elements like copper, metals, zinc, iron, but also sulfide are leached from rocks at these high temperatures. And then eventually these hot buoyant fluid, they rise back up to the surface where they emerge as hydrothermal vents, venting fluids like I just showed up to 400 degrees and forming mineral deposits when the hot fluids basically cool down and the solubility of metal sulfide is exceeded. So this is of course a very general model, but keep this in the back of your mind when we talk about the ways that we can use the isotopes today. So the sulfite minerals that we typically find in these in such deposits include iron sulfides like pyrrhotite, marcasite, or pyrite, basically depending on the chemistry of the fluid, temperature. Zinc sulfides like sphalerite, and if the fluids contain enough copper, hot enough, we can find sulfide minerals like chalcopyrite. Now, if we zoom out a bit more and actually look at how then these mineral deposits, these sulfides deposits change in size and, for example, copper grade, chemical composition per geological setting, then we see some interesting variations, as you can see here in these plots. So here on the left side, we have the average tonnage estimated, or for some cases measured per geological setting. And here on the right side, we have the average copper grade determined from measured samples. So what you can generally see already is that there's quite some variation between different geological settings. Generally, we get large deposits on the slower spreading ridges. I won't go into all those details today. But what I sort of wanted to take away from this slide is that that we have significant variations in the types, the compositions, and the size of the mineral deposits forming in these hydrothermal vents, suggesting that there might be differences in the chemical processes leading to the formation of these deposits. And so to try and understand why we have these variations, we need to focus basically on the reactions that are behind the formation of these mineral deposits. So in other words, we want to know basically what is going on below the seafloor, what is controlling why we have a lot of copper in some place and not so much copper in the other place. So if we want to study this from a geochemical point of view, then, well, of course, we can't go down there ourselves, so we have to rely on material that we can pick up from the actual from the seafloor. So we can work with hydrothermal fluids or with rocks that we can pick up from chimneys or from the mounds on the seafloor. Now, this is of course nothing new, and probably many of you following along are well familiar with this. But we can study, for example, the mineral assemblages in these rocks, or the chemistry of the chimneys that we pick up. Here are some examples from a study from the Lau Basin, where here are some images of mineral assemblages found in the chimneys. Here are some data from the chemistry of the chimneys. So this kind of information can tell us something about the conditions under which at which the deposits formed, or the conditions that were going on in the subsurface. Also here we have a plot showing fluid chemistry. This is another well-known technique of trying to understand what is basically going on in these systems. So here you see, for example, that we generally get quite higher copper concentrations the higher the temperature of our vent field. So that's great, but I promised you isotopes today. So why would we need isotopes in addition to this then? Well, stable isotopes can be used to provide additional information on sources and processes that are happening below the seafloor. And I thought to illustrate that with an example. So imagine that we find a chimney where we find pyrite. Then we can use thermodynamic models, like we see here an example, to derive what the presence of that mineral tells us about, for example, sulfide and oxygen concentrations. So that's great. That already gets us to some point. But if we then take our sample to the mass spec and measure the isotopic composition of that pyrite, then we get additional information on, for example, the sources of the sulfur. For example, was magmatic degassing involved? Was sulfur leached from sediments? And we also get information on processes. What was the extent of thermochemical sulfate reduction? Did minerals precipitate below the surface, or did we have mixing processes in the subsurface? And these are processes that we can trace then with the addition of isotopes to our concentration data. Now, as Christoph said, I have a background in Archean geology. So something that I would like to also highlight is that we can use these stable isotopes also in ancient systems. And this is great if you want to compare, for example, the size of modern seafloor massive sulfides with that of ancient VMS deposits, and try to understand why that size is why they seem to be different. So obviously we can't do that with studying vent fluids since we don't have them in ancient systems, but the stable isotopes, we can basically apply the same method and try to study processes back in geological time. So before I will then go on to show you some examples of how we can use these stable isotopes to look below the seafloor, I just want to take you all back to the basics for a minute and see why stable isotopes can be used in the first place. So basically, the key behind stable isotope geochemistry is that chemical, biological, and physical reactions, they change stable isotope ratios because chemical bonds with the light and the heavy isotopes have a different bond strength. So basically, bonds with the heavy isotopes are stronger than those with the light isotopes, and this leads to a change in the ratio of the two isotopes in a chemical reaction, for example. This is what we call fractionation. So I'm going to use that word many, many times today. Now we can have two types of fractionation. We can have equilibrium fractionation. This is the case for reactions where we have an isotope exchange. So we basically have a reaction going in two directions. For example, this is possible between sulfate and sulfide at high enough temperatures. And in this exchange reaction, what we then see is that the heavy isotope ultimately ends up in the strongest bonds. So isotopes are continuously exchanged, and then over time, the ones where they are bonded most strongly, that's where they're going to end up. So that can, for example, be solids or oxidized phases like sulfate here. Now, such equilibrium fractionation is something that we typically see at high temperatures because that's under those conditions, it's more easy to actually achieve isotopic equilibrium. And at the same time, the magnitude of this shift, this change in isotope ratios under equilibrium conditions is dependent on temperature. So this is actually the basis behind using, for example, oxygen isotope thermometers. So that's equilibrium fractionation. On the other hand, we have kinetic fractionation, and here we are dealing with what we call unidirectional reactions. So we're dealing with reactions that just go in one direction, and so there's no exchange going on. And in this case, again, it's the difference in bond strength that is critical. But now it's the isotope with the lightest bonds that is basically reacting faster. It's the bonds with the light isotopes are most easily broken. So the light isotope is going to end up in the products. Kinetic fractionation is something that we typically see in biological reactions, but also in fast chemical reactions where we don't have basically enough time to reach equilibrium. So, for example, if you would precipitate out a mineral really fast, for example, from a vent fluid on the seafloor, you could get kinetic fractionation. And so these things are going to come back again also today, because we will see that this is determining our interpretation of isotope signatures from hydrothermal systems, because we need to basically pick which of these two models is applicable to our isotope data. Something else that I quickly need to show you guys before we go on is this delta notation. So if you're not familiar at all with stable isotopes, this is how we express stable isotope ratios. We basically measure a ratio of isotopes in a sample and then normalize that against the standard. And then we express that in per mil. So this is this delta notation. And again, that's going to come back many times today. Okay, so then we've got the basics. So let's have a look then at stable isotopes in hydrothermal studies. So which elements show enough fractionation, or which elements are interesting to study in hydrothermal systems? Well, the days that this was just limited to what we now call the traditional isotopes, hydrogen, carbon, nitrogen, oxygen, and sulfur, they are luckily long gone. And thanks to analytical advances, we can almost measure any stable isotope in the periodic table. So here I tried to make an overview of which elements have been used in stable isotope studies related to hydrothermal vent fields. And if you basically take out all the elements that do not have stable isotopes, they're monoisotopic, or they have simply too low natural abundance to be measured. So these are all the grayed out ones here in this table. Then you can see it's actually quite impressive how many elements we've measured the stable isotopes already for in hydrothermal systems. And to be honest, probably the ones that I didn't mark, they might have all been measured as well. I just missed them when I made this compilation last week. But you can see, so there's a lot of elements that are suitable to use in hydrothermal studies. You can also see that not every element is useful for the same thing. So, for example, here, the fluid mobile elements, they are particularly suitable to study fluid rock interactions in hydrothermal settings. The redox sensitive elements, well, they're obviously most useful to study, for example, redox reactions, redox changes. The ones that are involved in life, we can study them to look at interactions between in more the lower temperature areas, biogeochemical reactions in vent fields. So you can see that basically there's a lot of possibilities in stable isotope geochemistry in applying them to study the processes in hydrothermal systems. Now, obviously, I can't cover them all today, so I will just focus on 3 of them today, and that's sulfur, iron, and copper, which happen to be the isotopes that I've been working with. And you can see that sulfur is really like there's really many possibilities that we can use sulfur for in hydrothermal systems. So I'm just going to highlight a couple of them. So sulfur has 4 stable isotopes, and we mostly use the ratios between the 32 and the 34 sulfur. And here you can see an overview of the sulfur isotopic compositions measured in bulk sulfite minerals from chimneys and in the sulfite in vent fluids per geological setting. So what you should take away from this is that you can basically see that spreading ridges, they have actually quite a similar range of sulfur isotopic compositions in their chimneys. Even their fluids are quite similar. And they basically all fall between the sulfur isotopic composition that we have for basalt and the sulfur isotopic composition that we know for seawater. So this is actually in itself already telling us something about the processes happening to sulfur in the subsurface. But we have 2 different models for that. So one way to explain this is by a mixing model. So this model is arguing that the sulfur is coming from both basalt, that it's leached from basalt, with a sulfur isotopic composition around 0, and that another component of sulfite is derived from abiotic sulfate reduction. And in hydrothermal systems, this is typically a quantitative process, so all the sulfate gets reduced, and therefore the sulfite that is produced has then the same isotopic composition as the seawater sulfate. So if you mix these 2 together, you get values between 0 and 21 per mil. And actually, if you would then take this sort of value of around +5 per mil for many of these chimneys, then you can just basically do a simple mass balance calculation and calculate that about 75% of the sulfite must have come from leaching from basalt and about a quarter from sulfate reduction. Now we also have an alternative model. This is the Anhydride buffer model. This is basically arguing that the sulfur isotopic composition of these chimneys, of the sulfite in these chimneys, is determined by equilibration with anhydride. So how this works is that anhydride forms when the fluids are on the way down and they get heated up. And then when the fluid basically is going back up to the surface, the sulfite in that fluid is equilibrating with the sulfate in the anhydride. And then depending on what temperature that happens at, that should result in an equilibrium fractionation factor of about 0 to 6 per mil. So there you go. And we have again the same sort of range as what we see in our vent fluids and our chimneys. And another way of explaining then what is why we see the sulfur isotopic compositions that we see. So 2 equally possible models, but how can we distinguish between these 2? Because that's of course what we eventually want to know when we are trying to look below the seafloor. Now this became possible when we started to look actually at the behavior of the minor sulfur isotopes as well. So 33 sulfur is what we call a minor isotope. this is an isotope that normally we wouldn't really measure. It has a low natural abundance, so it's analytically more challenging to analyze it. And the reason that we wouldn't measure it is because, in principle, isotope fractionation is occurring, or is a mass-dependent process. So basically, if we see a change, for example, of 2 per mil in the 34-32 ratio, then we expect about half a change for the 33-32 ratio because of the relative mass differences. So we can actually define a line along which all points should lie. For sulfur, that is this line. So this is a plot of the 33-32 ratio versus the 34-32 ratio. And this line is then defined by this slope of 0.515. However, back in the sort of mid-2000s, people realized that this value of the slope is actually not the same for all chemical reactions, and it can differ at temperatures. So if that happens, then that would basically produce points that slightly fall off this, our defined mass-dependent fractionation line, either above or below that line. And this is what we then started to indicate with this capital delta value that you see here. So basically, any point that plots above this line has a positive cap delta value, and any point that plots below this line has a negative cap delta value. So how can we then use that in hydrothermal systems? Well, Shuhei Ono's group then realized that for the anhydride buffer model, that this slope of 0.515 is not the same for all the temperatures at which this anhydride buffering would occur, and it's actually slightly different from this 0.515 value. So they calculated these values and then basically found this curve that we expect points to plot at if they are truly in equilibrium, in isotopic equilibrium with anhydride. On the other hand, the mixing model, this has nothing to do with isotope fractionation. So this is just mixing between basalt and seawater, and it's then just producing a straight line in this curve. So this use of this minor isotope then is a really clever way to basically distinguish between these two different models. And I'm just showing you here an example how this was applied then to the to sulfites found in the EPR 910 band field, where you can see sulfites here that are basically plotting on this mixing line. So the sulfur isotope compositions of these could be explained by this mixing model, whereas equilibration then with anhydride at 300 or 400 degrees is producing points that are falling off at either of those curves. So basically here you can see that sort of both models are operating at the same time, but with the use of these stable isotopes, we can try to pinpoint further what is actually going on below the seafloor. Now, for those of you that paid close attention to this plot, you might have seen that there are also some isotopic compositions in here that actually cannot be explained by this mixing model, because they're actually going to way too negative values to be explained by mixing between something at this point and something by mixing with something that has a composition of 0 and a composition of +20. Again, this is also telling us something about processes happening in the subsurface. So in the case of the Bergen basins, this can be explained by the fact that in Bergen basins, we're often dealing with more silicic magma, so we get degassing of SO2 happening there. And then when this SO2 gas cools down, it undergoes what we call disproportionation. So basically, it transforms into an oxidized and a reduced form of sulfur. And associated with that process is quite a large equilibrium isotope fractionation. And that is shown here in this figure. So if we start with a sulfur at this composition, then we can produce sulfide that is about 20-25 per mil lighter in its delta 34S value compared to what we started with. And so for Bergen basins, this seems to be then this then explains why we find values that are much lower the more, or than the mental values that we start with. So you can see this actually here. These are samples from the Eastern Manaus Basin, and you can see that they are plotting at values of around -5. So they are explained by this disproportionation reaction happening in the subsurface. There's also another cause of low delta 34S values in chimney sulfides, and this is basically the case for sedimented ridges, and this has a more low temperature origin or a microbial origin. This is related to a microbial process, microbial sulfate reduction. This is quite common in marine sediments, and here in this diagram you can see that this can produce really negative delta 34S values in the sulfide that is produced by the microbes. So if this process is happening in sediments, then we get sediments with quite negative delta 34S values. You can see here an example from a sturdy area in the Norwegian Sea, where we have sulfate reduction happening in the sediments, and you can see here that this delta 34S values are quite negative. And so what happens when these sediments are then, when there is interaction between these sediments and the hot fluids at depth, then these negative values are sort of taken, or are sort of, they become visible then in the vent fluid, because the sulfide keeps that fingerprint and sort of preserves that up to when it comes back to the surface. So in sedimented systems where sulfur from sediments react in the subsurface, we often see that this microbially produced sulfide is a cause for negative delta 34S values in chimneys. Now, I mentioned earlier that we can use stable isotopes also to trace processes in ancient deposits. So I just wanted to quickly show you this example that it demonstrates that we can even trace these processes many million years back in time. So this is an example showing sulfate reduction happening in a 3.2 billion year old hydrothermal barite deposit. And again, you can see that sulfate and that the sulfite has a much more negative sulfur isotopic composition than the sulfate. Again, explained by this microbial process that I was just talking about. So this is an example to show that that stable isotopes can be used in both modern and ancient settings. Okay, so in addition to sulfur, we can also measure the stable isotopes of iron in many sulfides. And iron is also generally quite present in vent fluid, so it's something that we can apply to our hydrothermal systems. So again, here is a plot showing variations in iron isotopic compositions now for bulk sulfides and vent fluids. And what is interesting to see here is that the vent fluids are all having a more negative or a lighter iron isotopic composition than the value that we have that we assign to basalts. And actually, there is quite a bit of variation also in the sulfite. So it seems that we have processes going on that are fractionating the iron isotopes substantially in the subsurface here. So how can we explain these shifts then relative to basalt? Well, just like with sulfur, this is a likely combination of several processes, and that's again also where it get particularly difficult to interpret these data. We basically start with leaching of basalt, where the lighter isotope preferentially leaches out. Remember, I talked about that. It's this sort of light isotopes sort of they react faster. The bonds with them are weaker, so they tend to be sort of more reactive. So in the basalt leaching case, we get a fluid that has a more negative isotopic composition compared to the basalt. And then after that, the iron may go through, for example, phase separation. It forms complexes for different chloride complexes, for example, and that is causing very small isotope effects. It can undergo a mineral precipitation reactions. So, for example, chalcopyrite precipitation or pyrite precipitation. So this basically means that the iron isotopic composition that we measure at the surface in our deposits or our fluids are again a sum of all these processes together. And so we can sort of try to do a bit of a back of the envelope calculation, use a simple scenario where we leach iron from basalt and then precipitate about half of that out on the seafloor from the fluid. And we can then, and so for this calculation, I've just, because these fractionation effects are quite small for phase separation and chalcopyrite, we've just ignored them for simplicity. But we can calculate then the isotopic compositions that we would expect for the fluid and the sulfite. And you can see that they're quite consistent with what we actually find in hydrothermal vent fields. So negative values for the fluid and then also negative values for the sulfites. But you can see that there's actually quite a big difference here between if we assume equilibrium fractionation or kinetic fractionation, and that is because these isotope effects are significantly different. Again, remember that has something to do with the way that this fractionation sort of happens in different types of scenarios under different conditions. So basically, what you can take away from this is, well, we can explain the iron isotope composition that we measure on the seafloor, but to really constrain what's happening below the seafloor, we really actually need additional geological constraints to determine sort of which of these models works best. Now that sounds maybe a bit negative, but I do want to show you then a bit more specific example of how we've tried to use iron isotopes to figure out what is happening at a vent field in the Norwegian Sea called Loki's Castle. This is a sediment-influenced vent field, basalt-hosted, and it is characterized by very low iron concentration in its fluids, as you can see here, even compared to other sediment-hosted or sediment-influenced systems, and particularly to other basalt-hosted systems. So what we try to do is use iron isotopes to then distinguish, to pinpoint these low concentrations to whether that was related to, well, maybe iron is leached from sediments, maybe there is subsurface precipitation going on, or maybe there's just very low solubility of iron in these fluids. So here is some data you can see from one chimney, and let's just focus some time on just the fluid composition here. Now, if you remember the isotope effect we just saw for leaching of iron from rocks, then if that would happen from sediments, then this changes. So this is the isotopic composition of the sediments at Loki's Castle. So the fluids are not very different from the isotopic composition of the sediments. So it seems not, it doesn't seem to be consistent with just simply iron leaching from sediments and then coming up back to the surface, simply because the isotope effect that we see, that we think should happen is not what we see. So can we then maybe attribute this to mineral precipitation? Well, again, we can make sort of a fairly simplistic model for this. So if we take a fluid, say we start at 200 micromolars of iron as a starting point, and then we can calculate the isotopic compositions that are expected for the fluid if pyrite was precipitating below the surface. So this is what is shown here for different scenarios, for if we leach it from sediment or from basalt. And then the lines here in the bottom are the case where we assume equilibrium fractionation, and here at the top where we assume kinetic fractionation. So if we compare this then with the value that we find at Loki's Castle and the concentrations at Loki's Castle, then, well, it seems to be consistent with that we have subsurface precipitation of pyrite if we assume that we have kinetic iron isotope fractionation, because this is basically where our lines are intersecting with our fluid composition. So that's great. That could explain then why we have low iron kinetic fractionation during subsurface pyrite precipitation. But we then have to think again about, well, this kinetic process, this is something that we typically see that is associated with unidirectional reactions. So it would require that there is no recrystallization going on, there's no equilibration going on between the the iron in the fluid and the iron in the precipitated pyrite, because the isotope effect for that would suggest that the fluid should become basically heavier in its isotopic composition. So the conclusion is it's not very satisfactory in that sense. We can't really exclude one scenario or the other. But it seems that it's maybe difficult to explain it with just subsurface precipitation of minerals, because it seems unlikely that at high temperatures you would not have this equilibration happening, at least to some extent. So yes, a little bit, it's not really a watertight sort of explanation. What it does make it very clear, though, is that it's absolutely critical for such interpretations to have these numbers of these isotope effects. So to have experimental or theoretical constraints on the isotope effects that we can expect, such as the number that was used here. Without that, it's almost pointless to do these kind of exercises. And that is even more the case for the last isotope system that I quickly want to show you, copper isotopes. Because here you can see, for example, from the fluid data that we have extremely little data points, and even the solids, the sulfides, if you compare this to the 1700 data points that we have for sulfur, then for copper, we're only, I think, about 120 or so. So we really know a lot less about these sort of new isotope systems. And this is, of course, hampering, to some extent, also our interpretations. So what is interesting here is that the fluids, the data that we do have, are more positive than our basalt. So this is the opposite from what we saw for iron. Actually, we just added, like in the last few weeks, a couple of data points from the magnesite, seemingly confirming this +1 value for vent fluids. So here is quite a narrow range, it seems. The deposits, they show a much larger range, and the origin of that is tricky to explain. But as I said, we're getting more analysis are being done, and more experimental data is also now being published. So hopefully we'll be able to give a more sort of satisfactory presentation about this in a few years' time. We do have some data, so we know chalcopyrite pyrite leaching produces fractionation, but the two estimates are really quite different, from very negative, from say -1 to +1. So the +1 value could, of course, potentially explain our fluid data, but then the -1 is we don't really know what to do with that. Chalcopyrite precipitation, we know, is not really causing much fractionation, so that can't really explain the range that we see, for example, in the sulfite deposit itself. So some other possibilities that I think we should really explore further in experiments to try and see if this could contribute to the fractionation observed in nature. Phase separation, so during boiling, when there is a change basically in the chemical environment for copper, when copper can go into different types of complexes, there might be a fractionation going on there. This is what has been predicted from theoretical calculations. So different copper complexes having different isotopic compositions. Maybe that's explaining something. So maybe this would be a way to trace then the behavior of metals during phase separation in hydrothermal systems. Or maybe the variations that we see are just a result of basically processes happening kind of at the seafloor. So not really subsea floor processes. Because we do know that the largest cause of copper isotope fractionation are oxidation processes. So maybe the values that we see are just a result of the formation of secondary copper phases and then interactions of the fluids with them. So you see, there's really still quite a lot of work to do here to make copper isotopes as useful as a tracer like sulfur isotopes. But I think there's a lot of potential. So then to sort of summarize or to sort of conclude, lots of possibilities, but also lots of challenges seen today. So what is then needed really to make stable isotopes a perhaps even more powerful tool for seafloor studies? Well, I'd just like to share you my ideas on this. So I think that Every isotope tells basically its own story, as we've seen today. But many of them are, of course, connected. If you have pyrite precipitation, you should see that both in iron and in sulfur. So I think combining these different isotope systems is really the way forward, and that might give us more certainty on the interpretation of the processes happening. And this includes, of course, adding new isotope systems that we've maybe not explored so much today, obviously only for the ones that actually make sense that are actually interesting for hydrothermal systems, but we've seen many of them are. But in addition to that, probably more critically, what I just mentioned a few minutes ago, it is absolutely critical that we get better fundamental understanding of the magnitudes of these isotope effects that we can expect under hydrothermal conditions. So we need more experimental work or theoretical work to do this. A lot of great work has been done in the last couple of years, but it's absolutely critical to interpret our data from natural systems. Having said that, we can, of course, also obtain a lot more knowledge about these new isotope systems by basically sampling a wide range of hydrothermal vents, taking good care that we're not causing isotope fractionation during our sampling process itself, and basically trying to get a better idea of how isotope signatures change systematically per setting. And of course, we can apply the same isotope systems to VMS deposits, and that would even expand our database further, of course, and perhaps help us answer these questions like, as I said in the beginning, why modern seafloor massive sulfides seem to be different in their composition and their size from ancient VMS deposits. And stable isotopes are really great for that because they get preserved most of the time in the rock record. So a lot of possibilities, exciting possibilities, I think. But the last thing I want to say about isotopes is that it's important to remember that they rarely seem to provide sort of smoking gun type of evidence. We almost always need some other data with that in addition, like we saw, for example, with the iron isotopes today. So it's absolutely critical to use them in a bigger framework of other geochemical and geological data. So with that, I leave you with something that is actually smoking, and a big thank you to all the people that have contributed to all the work in this presentation.
Okay, thank you.